So I just wanted to talk a little bit about these integrals that have x to the p in the denominator and when they converge or diverge. So really what's important to know is that the transition point is f of x equals 1 over x, which is where p equals 1, because it's 1 over x to the first power. And so what's important to know about this function is that it approaches both axes at the same rate. So it crosses here at 1, 1, and then it has a graph that looks like this. So if we were to solve this for x, we would get x equals 1 over y. So you can see that these two functions are basically the same, right? One is a function of x, one is a function of y, but this approaches the vertical asymptote at the same rate that this approaches the horizontal asymptote. And we actually showed in a previous video that the integral from 1 to infinity of 1 over x dx tends towards infinity, so it diverges because this area is infinite, and thus the integral from 0 to 1, which would be this area right in here, also tends towards, oops, I should write 1 over x dx, also tends towards infinity. Now technically from 1 to infinity should be slightly smaller than from 0 to 1, because I'm including this piece right in here, right? If I was actually going to cut it in half, it would have to be there, but that would be a little challenging to do. But it doesn't really matter because they both tend towards infinity, so who cares? So 1 over x is the one that just basically does not converge no matter what you do. It's the transition point. Now when we start changing those p-values, what's going to happen is that one side is going to get closer faster while the other one is going to get closer more slowly. So let's take, for example, the classic g of x equals 1 over x squared. Now p equals 2 in this case. So as we plug in values for x, it still crosses at 1, 1 right there. But now when I plug in 2, I get 1/4, which is quite a bit less than what it was up here, which was 1/2. So it's going to come down quite a bit faster here and get closer to the axis much faster, the x-axis. But on the other side, it actually doesn't approach as fast. So this area right here is much smaller than this area. This is much bigger. And so what we know in this case is that the integral from 1 to infinity of 1 over x squared dx actually converges. I think it converges to 1, but I forget. And then the integral from 0 to 1 of 1 over x squared dx, it diverges. Okay, and that's because this area is now quite a bit bigger than this area, and this area is even bigger than the one that we had for 1 over x, so it definitely diverges. If we were to take this function, which is, y equals 1 over x squared, and solve it for x, in this quadrant we would get x equals 1 over the square root of y. So you can see that that is now behaving like 1 over root x if it were down here, which does not approach the axis as fast. We could do something similar if we wanted to with, we could say, well, what if h of x is equal to 1 over the square root of x? Then it looks like sort of just the reverse of what we had up here, where it is going to still cross through 1, 1, but approach this y-axis very quickly and the x-axis very slow. So now our area here is much bigger. And here our area is much smaller. And again, here is where p would be 1/2. And if I solved this for x in this quadrant, I would get x equals 1 over y squared. And so that is now approaching the axis, this axis, much more quickly. So now we know that the integral from 1 to infinity of 1 over root x dx diverges, but the integral from 0 to 1 of 1 over root x dx converges. So to summarize, we can basically say this. For the integral from 0 to 1 of 1 over x to the p, this converges for p is less than 1. From 1 to infinity of 1 over x to the p dx, this converges for p is greater than 1. And for something like this, it really doesn't matter where we start. Because if I start, say, at, 10, that will also converge because I'm just basically getting rid of a finite amount from 1 to 10. So it's still going to converge. And similarly, up here, if I went from 0 to 0.1 of 1 over x to the p, this would still converge for p is less than 1 and diverge otherwise because I'm still dealing with that vertical asymptote. So that should give you a sense of when these converge, and I think what I'm going to try and do is look at some Desmos graphs and sort of show this area graphically.